Okay, again, I saw this problem on the internet. I thought it was an interesting problem. It says solve. You notice that link is available to you if you want to look at somebody else solve the problem. Solve this problem, which is x to the 10th power, which looks like a flattened parabola, and then an exponential 25 to the x. And where are they equal? And they say x is a real number. It says one solution is obvious, but the other two are probably going to need a little thought. All right? So I will go to the whiteboard and talk about the obvious solution, and then I'll talk about why it's so difficult sometimes to find the other two. All right. Now, the guy that does the video, again, it's linked over here. He uses the Lambert W function, which appears to be quite popular nowadays on the internet. I notice a lot of people doing it. I would say that most curriculums, at least the ones I'm familiar with, do not talk about that. All right. Like, for example, where I teach, I think even the faculty members would probably not know about the Lambert W function. And certainly the students are probably not aware of that either. But anyway, it's something that's around and something that you probably should be aware of. And I would recommend that you watch the guy solve the problem. I'd also recommend you follow this link over here and maybe read up on the Lambert W function. All right. Now, again, I give you the SAGE code for finding solutions to those two problems. And the reason I'm giving the SAGE code is I want you to learn how to use a computer algebra system to solve problems. And these are approximate solutions. So I go through that, and there's a link there for the SAGE code if you're interested in doing that. All right. So I go through the SAGE code for both of these problems over here. What I mean by that, there's two places where they intersect, and we'll talk about that in a moment. Now, I want to point out for me to come up with these things over here, and when I do a paper and pencil sketch, it's really kind of tough to determine what the points of intersection are. But there's actually three of them, and one occurs here, and this pink curve is the function y equals x to the 10th power. I say it's a flattened parabola. It's not a parabola, but to me it looks flattened parabola. And this green curve is the exponential, y equals 25 to the x. So I'm going to say, I see a solution over here. I'm not sure what it is, but, maybe roughly about minus 0.7. All right. And then what I did, I found another solution where it roughly, intersects. It's roughly over here. Again, when I say roughly, I'm looking at the picture. I'm not exactly sure what happens. But I got numbers down over here, 1 and 2. And if I look at that, I'd say maybe 1.7 then. All right. Now, granted, there's another one. I don't have it graphed out. And the problem with the graph, and I'll go to the whiteboard in a second, is they can be deceptive. All right. Let me go to the whiteboard. And what I mean by that, if someone said, solve the equation, x to the 10th power equals 25 to the x, in my mind, I'm sort of visualizing, and I'm visualizing this first, and this would look, I'm going to say, look sort of like this to me. And I'm not doing a terribly good job. I want to point out, it looks like a parabola to me. It's not a parabola, it's flattened, but it doesn't look like a parabola. And then I'd say, this guy over here is exponential, and I would say, yeah, I see it hitting over here. And then I'm saying, it's probably going to go jamming through that at some point, all right? But that's where I got deceived, by the way. I would say, there's only 2 points of intersection, all right? There's actually 3, all right? And again, I would recommend investigating this thing graphically. And what I mean by that, not by like paper and pencil graph, I mean using a tool. Like I use Grapher, you might use Desmos, you might use your handheld calculator, whatever. But let me talk about the easy solution to the problem. And when I first saw it, I saw it on YouTube. I saw the thumbnail, and the thumbnail was this thing over here. And I'm thinking, that's got to be an easy question, by the way. And the reason for that, I kind of look at it, and the way I would do it, again, it might differ from person to person, but I would say, that's 2 times 5. And then I'd look at this thing and say, 25 is 5 squared. And I kind of play around with this. I'd say, x squared to the 5th power. That's 5 times 2, by the way. And then over here, I would say 5 squared to the x power. I really haven't changed it much. Now, looking at it, I'm going to say it seems somewhat obvious now that the x is 5. Let me point out what I mean by that, somewhat obvious. Like if I do the left side, it'd be 5 squared to the 5th power. And what's the right side? 5 squared. And again, x is 5. It's true, all right? Now, granted, if you want, you can compute the numbers. These are really big numbers, by the way. For example, if x is 5, if I plug it into this equation over here, what do I get? I get 5 to the 10th power. really big number, by the way. And then I get 25 to the fifth power. And they're the same number, all right? And that's about it. Again, when I go back over it again, I want to talk about, I will be going through what I've been repeatedly doing in the notes, by the way, at least for this document. You know, I've been using Newton's method. I think it's an important numerical technique, and one that's really easy to code, by the way. It's also fairly easy to understand if you know calculus. If you don't know calculus, it's still fairly easy to implement. And my understanding is Newton's method was once taught as a way to find roots. And now what I mean by that, it was once taught to find like the square roots of 2, the cube roots of, whatever, 5. It was once used to do that, by the way. It's a numerical technique. What's nice about a numerical technique, it really lends itself nicely to a calculator, all right? And I'm using this on a computer, but I'll go through that with the link for both of these, all right? Thank you.